Okay, back to it. Today's going to be part 2 of your logarithm notes, at least the introduction to logarithm notes. There will be lots more logarithm notes. We still have to do graphs and word problems and properties of and solving and all kinds of fun stuff with them. Semi-log plots, all kinds of good stuff. But for now, we are mastering the basics of logarithms, understanding what they are, how they work, why they do what they do, and tips and tricks and things like that. Okay. Boop. Alrighty, so we talked about it yesterday, but we didn't do much with it. The common log. Remember what I was telling you yesterday, that our number system is base 10, and because our number system is base 10, the most common logarithm we use is log base 10. So common, in fact, that we don't even have log base buttons on our calculators. They just say log. The assumption is, most of the time, you're going to be doing things with just your standard common logarithm. That is base 10. So we're going to be evaluating these 4 common logarithms without our calculator. And let me remind you what log says. Log says, what power of this base would get me my argument? Here the argument is 100. The base isn't written, which means the base is automatically 10. And remember, a logarithm can only do its job if the base of the logarithm matches the base of the argument. So I have to be able to write 100 as a power of 10. Lucky for us, it is a power of 10. It's 10 squared. So you could have just said to yourself, what power of 10 gets me this 100? And the answer is 2. Or you could convert your 100 to 10 to the second power, and then let log base 10 do its job, canceling exponential base 10, leaving you with a value of 2. Either way, it's fine with me. If you weren't here yesterday, I think it was only one of you. If you weren't here yesterday, you're definitely going to want to watch yesterday's video. Get caught up on logarithms. Now this one. Square root bar is an exponent. What power is it? Lots of voices, please. 1/2. The index is 2, but it's a 1/2 power. So what we have here is the common log, so log base 10 of, instead of saying root 10, we will say 10 to the 1/2 power, allowing log base 10 to cancel exponential base 10, dropping the 1/2 out of exponent position into simply answer position, 1/2. Done. There it is. So like I said, a logarithm can only do its job if the log base matches the argument base. This is base 10. I need to write 1 over 1,000 as a power of 10. Not that hard to do. As long as you remember that negative exponents flip fractions over. I can say that 1 over 1,000 is actually 10 to the negative. It has 3 zeros, so negative 3. We now have log base 10 doing its job, canceling exponential base 10, leaving us with negative 3. And the last one, don't fall into a trap. Exponential base 10 does not cancel log base 6. So the answer is not 6. What does log base 6 cancel? Exponential base 6, which means right here, I have this log base 6 canceling this exponential base 6, leaving that power of 1. Leaves me with 10 to the 1, which is just 10. If you recall yesterday's property, log base b of b always equals 1. So log base 6 of 6 is instantly a 1 up there. Talked about tips and tricks. A pattern that I picked up on a long time ago, and maybe you did too, is that anytime you're working with things like this, where the argument and the base, one of them is a fraction and one of them is not, you're always going to get a negative result, because the result is the exponent that made it happen, and negative exponents flip fractions over. And that's what happened right there. You guys cool with that? All right. So for number 5, A, B, and C, it says to evaluate with a calculator, but before I touch the calculator, and I don't even need to do anything special, I can use a scientific for this one, but before I touch the calculator, I like to just see if I generally have an understanding of what the answer should be. This is the common log. It asked me what power of 10 would get me a 34.5. Clearly the answer is not going to be pretty. What power of 10 would get me a 10? 1. What power of 10 would get me a 100? 2. This argument, 34.5, is between the numbers 10 and 100. That means it is between the first power of 10 and the second power of 10. So this answer had better be between 1 and 2. This is AP, so we'll go to 3 decimals. $1.538. 1.538. Something going wrong in the calculator back there? He's working ahead? Okay. So the reason why, I'm just going to re-explain, I'm going to write it down. The reason why I expected an answer between 1 and 2 is because 34.5 is somewhere between 10 squared, which is 100, and 10 to the first, which is 10. So I expected an answer between this power and this power. And that's exactly what I got. Let's use the same kind of knowledge on this one. 0.43. Well, that's definitely smaller than 10, which is 10 to the first. But you know what else it's smaller than? 10 to the 0. What is 10 to the 0? 1. 0.43 is less than 10 to the 0. It's less than the number 1. But it's greater than 0.1, 1/10, which is 10 to the negative 1. That means the power that gets a 10 down to a 0.43 is between 0 and negative 1. I'm going to get a negative answer. The moment your argument is smaller than the number 1, you are always guaranteed to get a negative result. Well, okay, that's for the common log. So for the common log, if your argument dips below 1, you're guaranteed to get a negative result. Because 10 to the 0 is 1. Let's see what we get. Log of 0.43 is negative 3.67. 0.367. I couldn't remember if I said the decimal or not. And what power of 10 would get you a negative number? Let's see what the calculator says. Do you see what kind of answer it just gave me? What kind of answer did it give me? It gave me an imaginary answer. A complex answer? I wonder why it did that. You know why? It's because I'm in complex mode. Let's see what happens if I take it, whoops, wrong button. If I take it back into the real number system only, and I try that again. Oh, crap. Error. Undefined. I mean, I can tell you why that happened. Yeah. 10 is a positive number. You could raise a positive number to any exponent you want. You're always going to get a positive result. So using that knowledge and the answer that we got for this, what general statement can we make about logarithmic functions? More specifically about the argument of the logarithm, the inside. What do you got for me? The argument can't be negative as part of it. So if it can't be 0, it can't be negative, what do we need to say? Well, the base has to always be positive. So that's part of the general rule. So what just happened here? What has to be positive? Argument. Okay. So I don't know if you guys realize this, but the argument is the input of the log function. Did you guys catch on to that? And inputs are our domain. So the domain is only positive numbers. Argument must be positive. So domain is from 0 to infinity. You know why the domain of the logarithm function is from 0 to infinity, not including 0? It's because that's the range of the exponential function. Remember, logarithms and exponentials are inverse functions. The domain of one is the range of the other. So because the range of exponential functions is from 0 to infinity, non-inclusive, the domain of logarithms is from 0 to infinity, non-inclusive. Ta-da! It all comes together. Cool beans, huh? It should make sense. And if you want to know the range of logarithms, it's the domain of exponentials, which is all real numbers. Okay. This is fun stuff. Evaluating logarithms without a calculator, making you feel big, fat, juicy brained. Okay? If you understand what a logarithm says, if you understand its set of instructions, then this is actually very easy. This set of instructions is, what power of my base gets me my argument? So what power of this 2 gets me a 32? 5 it is. But the reason why it's 5, the answer is 5, yes. The reason why it's 5 is because log base 2 can only work on exponential base 2. And 32 happens to be a number that can be written as a base 2 number. Because the log base 2 and the exponential base 2 cancel each other out. I mean, that's pretty darn convenient. But this, what power of 49 gets me a 7? And there is a power that does it. 1/2 power. Why 1/2 power? Oh, what? Would you use your calculator? Because it's the square root, thank you. Because 7 is the square root of 49. So the 1/2 power, which is square root, would get us this 7. Okay, let's approach this a little bit differently though. Let me show you how I teach it in Algebra 2. And I'm going to do my best to fit it in this box. I'm going to make it small, okay? The way I teach my students to be able to evaluate logarithms before they get really, really, really good at them is I use exponential functions instead of logarithms. They go, all right, let's do it like this. Let's say I can evaluate this without a calculator. That means there's a number there I can find. The problem for students in the very beginning is that logarithms are a little bit confusing. And I go, fine, let's work with something that's less confusing for students. Let's work with exponentials. Let's make the logarithm go away because that seems to be what's causing problems. We cancel the log base 49 then using exponential base 49. So we put an exponential base 49 on both sides, like this. On the left side, what happens is the base 49 and the log base 49 will cancel out. And you're left with 7 equals, and on the right side you have 49 to the x. You should have done these in Algebra 1. Now your teacher might not have gotten to it, or you might not remember it. That's okay. But the way they teach you to do this in Algebra 1 is, since you have no other options, to make both sides have the same base. Lucky for us, 49 is a power of 7. So they're both powers of 7. Specifically, 7 to the first and 7 squared. Oh, that's right, there's an x though. But if you recall from before the break, when you have a power to a power, you multiply your exponents. So what we have here is 7 to the 1 equals 7 to the 2x. And in Algebra 1, they perform a bit of magic and tell you, since the bases are equal, you can just set the exponents equal to each other. But is that an algebraic process, what I just said? No. It's a trick. So what algebra allows me to discount and not care about the exponential base 7s? Log base 7. If you took log base 7 of both sides right now, the exponential base 7s would cancel off of both sides, leaving you with 1 equals 2x, and then you could divide both sides by 2 and get the unknown value x was 1/2. So that was a lot of algebra to prove to you that you could just say what power of 49 gets you a 7. But this is how you would do it if you didn't instantly see the answer. You could just use algebra and exponential functions. But you know what? I don't do that. I teach my students to do it. I make them do it a few times, like I'd make them do it again right here. And then eventually I go, doesn't it feel like there should be a better way than assigning some variable x and solving for x? Yeah, he hit his head on that chalk tray back there, dry erase tray. I saw that. I saw it. I saw you hit your head on the tray. Yeah, I didn't miss that. Yeah, the video's still going. I just wanted to make sure that it was, enshrined in all infinity that I saw you hit your head. Anyway, there's a better way, guys. There's a better way. It's literally a shortcut. I'm not going to show you why the shortcut works right now because I haven't reviewed the properties of logarithms that show you why it's true. However, you just saw that algebra could do it for us. So here comes, and it is legitimately a trick. The trick is get the log base and the argument base into powers of the same number. The base of the logarithm can be written as a power of 7. The argument can be written as a power of 7. Log base 7 cancels exponential base 7 and leaves you with the 1 over the 2. And that is a trick. I haven't proven to you that it works. I've showed you it working using algebra, but that is not a proof. A proof requires me to use properties and not use numbers. We'll do that eventually, but for right now, here is the overall property that I'm teaching you. And I'm okay if you use it. I'm all right with that. Log base b and exponential base b canceling each other out, leaving behind just the exponents. I'm okay with that. You know what's neat about that, though? I was never taught that in school. Ever. I was not taught that in high school. I was not taught that in college, earning my degree in mathematics. I didn't know it until I was an Algebra 2 teacher some years ago. And guess what taught me that? A cheating student. A cheating student. You see, cheating. You see, this is not in our textbook. Well, we don't have a textbook because this is AP, but it was not in the Algebra 2 textbook and still isn't. Like I said, I'd never seen this anywhere before. It's a truth and I can prove it. So I assigned my logarithm homework to Algebra 2 regular student, and when it gets turned in, it has math like this on it. And I'm looking at it and I was like, okay, That's a neat trick, and it's obviously true, and I can see why it's true. But I didn't teach this student this. So I called my dude down at Northport, and I was like, hey, dude, have you ever seen, and I described to him, and I basically told him, write this. And he's like, well, it's obviously true. I said, yeah, I know it's obviously true, but that's not the point here. The point is, that's not how I trained my students. Where did he see this? And he was like, bet you it was photomath. Scan the problem with photomath and see what it does. And this is back when photomath would show you the work for free. And that's where the student got it from. And so I learned it from photomath via a cheating student. And I was like, okay, cool. I mean, it's a truth. And I'm comfortable with my students using this truth if they could get there without the trick. And this was what I taught my Algebra 2 students to do. Because it was important to me that they understood the inverse properties, bless you, that logarithms bring to the table. Again, you've known me for a little while now. I'm not a fan of tricks unless you know why that trick works. And I think that you could all pull that off. Therefore, you have an understanding of why the trick works. Not a perfect one yet, but after I've reviewed with you the properties of logarithms, I'll be happy to prove that one for you. Okay? All right, now, let's use that trick. And let's evaluate this logarithm using easy math. We need 1 over 64 and 4 to be written in the same exponential base. What exponential base do they both have? 4 is one of them and 2 is the other one. It's what's neat about the numbers 4 and 64 is that they share two different exponential bases. The nice thing is it doesn't matter which one you choose, you're going to get the same answer regardless. So let's do the more difficult one first. Let's use base 2. And the only reason why it's more difficult is because 64 is a larger power of 2. No big deal. But if you know the power of 2 that 64 is, it's not a big deal. 64 is 2 to the what power? 6th. So 1 over 64 is 2 to the what power? -6. There you go. Because the negative exponent would flip it upside down, right? Well, not flip the fraction upside down, but would move the 2 across its own fraction bar. And 4 happens to be 2 squared. So if you allow log base 2 and exponential base 2 to cancel each other that way, which is a trick, that is not true algebra that you just saw me do with that purple pen. It's a trick. You would get -2 over 6, which reduces to -1/3. But the easier thing to do when two numbers share an exponential base is to choose the larger one. That's always less work. You won't have to reduce a fraction if you do that. And the base they share, the bigger base they share is 4. So I could have written it as log base. 64 is what power of 4? Come on, guys. 4 to what is 64? The third power. The third power. So this could be written as 4 to the -3. And the argument of 4 could be written as 4 to the 1. So when the log base 4 cancels the exponential base 4, again, what you just saw me do with the orange pin was a trick, you'd be left with -1/3. So it doesn't matter which one you choose. You're going to get the same answer. But I just wanted you to see that it works either way. And this last one, undefined because the argument can't be negative because that is outside the domain of the logarithm. This is undefined. Now I want to throw a curveball at you. Don't touch your calculators. So it seems like 2, doesn't it? Because -5 squared is +25. But if you put that on your calculator, no, it's not 1/2. 1/2 means square root. Square root of -5 is nasty. But if you put this on your calculator, oh, we haven't reviewed how to do log base on the calculator yet, have we? We haven't. Well, it was going to be the thing that I showed you next in the notes. If you press the math button, somewhere on that list, and it's different for different people's operating systems, somewhere on this original list, it'll say log base. So it's in math. Math, and then somewhere in there, there's a button that says log base. Now this log base, I'm going to type -5. We all know that -5 quantity squared is 2. Is 25. So why didn't the calculator tell me that the answer was 2? Why did it tell me that this is also undefined? Well, because of the exponential function, the rules about the base of an exponential function is that the base of the exponential must be positive, which means the base of the logarithm must be positive. Because even though -5 quantity squared is 25, this is not a graphable function. This is not a function because it will be undefined at every even fraction exponent, because those are all going to be the second root, fourth root, sixth root of a negative number, which is imaginary. So this is not a function because it breaks the rules of the exponential base. So if it can't be part of the exponential base, it cannot be part of the log base either. Yes, sir?
Why is log base 10 the most common?
Because our number system is base 10.
But what does it mean, like, most common? Like, what?
It means most of the logarithms that you're going to work with will be log base 10 because you're working with our number system.
Like real world problems?
Yeah, like real world problems. Because our number system is based on powers of 10. Like you have the ones place, this was 10 to the zeros. You have the tens place, which is 10 to the ones. You have the hundreds place, which is 10 to the twos. Literally, if you write the number 123, what you are saying is, I have 1 10 squared and 2 10 to the firsts and 3 10 to the zeros. These are the ones, these are the tens, these are the hundreds. I have 3 ones, 2 tens, and 1 100. So our entire number system is base 10. Yes?
We can't take like negative square roots.
Wait, you mean...
Like if I can't take, do you know the little number that we call it, that we have cube roots?
You mean a negative index?
Yeah.
You can, but it's not the way you're thinking about it. Here, I'll show you. This doesn't make any sense. But what this means, what you mean by this is this. Right? But that's this.
So we can do that, but I just want to know.
This is the exponent. The exponent could be negative. But the result of every logarithm evaluation is actually an exponent. You see, this was saying, what power of 2 gave me a 32? The result is an exponent. The exponents are allowed to be negative. The bases are not. And this is the base of the logarithm, and this is technically the base of an exponential. Okay? Yep. No clue. If it doesn't have log base in math, then it might not be able to do it. You don't understand why what? It's important, ask. Okay, don't phrase it in words. Tell me a question that you want me to explain.
It's okay.
No, it's not.
I'll think of a way to ask the question, and then I'll talk to you about it.
Okay. All right, we'll try. Yep.
So then there's no way to find the exponent of a negative base
Through
through logarithms?
logarithms, not in the real number system. So if you did this is doable, but not in the real number system. If I put my calculator back into complex mode, it'll give me an answer for this. So it has complex results, just like this has complex results, but they don't exist in the real number system. In fact, now that you said that, I'm curious. No, mode. Let me go back into complex mode, and let me hit enter. And look, the answer's not 2, is it? But it does have a complex answer. And eventually this year, I can explain to you what this complex answer represents and where they come from using trigonometry, but I won't be doing it using logarithms. Okay?
So anytime you see that from like logarithms, you just write like undefined.
If you see a negative base or a negative argument, undefined. If you see a 0 base or a 0 argument, undefined. If you see a 1 base, undefined. The argument's allowed to be 1 because, where the heck is it? Right there. So if the argument is 1, it automatically equals 0. But the base can't be 1, and neither the base nor the argument can be 0 or negative. Both the base and the argument must be positive, and the base cannot be 1.
Can the base be 1 if the argument is also 1?
Nope. Log base 1 of 1 is still technically undefined because it has more than one answer. It could be 1 or 0 because 1 to the 1 is 1 and 1 to the 0 is 1. So the moment you do log base 1, it doesn't matter what you type, it's going to go no. And that was even in complex mode. It said, no, you just tried to divide by 0, which is really neat. Whereas we all go, yeah, I feel like it should have 2 answers. The answer should be 1 and the answer should be 0. Oh, it should have 3 answers. -1 works also. So does 5. So does 8. Actually, infinite answers. So that's the problem. It has an infinite number of answers. 1 to any power always gives you 1. So that's why we don't do that. Okay. Boop. Is this where I was?
No.
Yes. There we go. Use your calculator to evaluate each one to 4 decimal places. And I kind of let the cat out of the bag. We already know how to do it. If our calculator does it. Math, somewhere in there is log base. So log base 3 of 15 is, it says to 4 decimals, but oddly enough, if you go to 4 decimals, it's going to round to 3 decimals. So we get 2.465. And I want you to think about why this answer makes sense. I want you to think about it. 3 to the 2 is 9. 3 to the 3 is 27. And this number is between 9 and 27. That's why this answer is between 2 and 3. Let's see if we could predict what 2 integers this one's between without our calculator. He says 2 and 3. 4 squared is 16. This is bigger than 16. 4 cubed is 64. This is smaller than 64. So clearly this answer is going to be between 2 and 3. $2.929. Let's get these last 2 knocked out. Okay, this one's a little more challenging. 0.35 coming all the way up to an 8.4. All right, let's talk about this. 0.35. That number is between 0 and 1. So what kind of powers would I need to use to get it to a number that's larger than 1? Negative powers. So we're expecting a negative answer. 0.35 to the -1 would be 100 divided by 35, which is almost 3-ish. So I'm expecting a number between -1 and -2. That's what I'm expecting. I actually don't know because I didn't do this one with second period. Oh, even past -2. It was an estimate because I used, I said 100 over 35 was about 3. So yeah, -2.027. I'm going to use 3 decimals. This is AP. I'm not going to 4 decimals. -2.027. AP wants 3. I'm using 3. And then this one. 5 over 2 is 2.5. He hit his head too. That's 2 different people hit their head during this class period on that marker tray. You know, if this was like the first week of school, I wouldn't be surprised. But this is the 19th week of school. We're still not knowing how close we are to the marker tray back there. Whatever. Math. Log base. I'm going to do 2.5 if you don't mind. You know what? Nah. Let's have some fun with it. Let's do alpha y equals stack fraction base. Now before I hit equals, I want to test my own knowledge and my own estimation skills because I am a big old nerd. 2.5 is between 2 and 3. 2 to the 8th power is 128. So is that 2 to the 7th? Did I say the wrong? 6. Oh yeah, 7th. 2 to the 7th is 128. But this number is bigger than 2. And 3 to the 7th, yikes, is huge. I'm suspecting our answer is around 5-ish, if I had to guess. Huzzah! God, I'm a nerd. This is like an actual depiction of me. Anyway. 5.269. I think we're going to call it there, nerds. That's a good spot to stop. We'll finish the notes tomorrow.